problem set because we had the Clemens competition last Saturday. So we kind of felt like that should have served as your problem set. Um, so that's kind of like a perfect transition for us to go into like start trying out lectures, which is where we would like go like more in depth into a specific concept. So today I'll be going over hashing, but we will like in like the few upcoming meetings, we will also try out some more different topics. So yeah, then at the end of the meeting, I'll like send like a survey for you to like feedback about like if you like lectures compared to problem sets or like what we could do to improve lectures. So okay, I'm gonna share my screen. So basically, you can find this like if you don't already know, we have this public drive. Let me actually send a link to it. But basically, I think the the bit.ly is like bit.ly.cs club drive. Yeah, I'll just type that in the chat. Okay, so the link to the drive is, so this is a public drive and you can find like our club resources. So like if you go to advanced, here are all the meeting solutions and stuff. And then today's like lecture is the PowerPoint is here. Okay, so that's what this PowerPoint is. Okay, so we'll start with what is hashing. Hashing is a way of encoding a string as a number. So hashing has some pretty interesting applications in things like file security and message encoding and data retrieval. But in this presentation, I will show you how hashing can be useful in competitive programming. So let's start with comparing two strings, right? Checking if two strings are equal. So Java has this method called .equals, which checks if two strings are equal to each other. But let's say that we were trying to write the method, right? We didn't have the built-in method. How would you check if two strings are equal? You would first have to make sure that their lengths are equal, right? Because if the strings have unequal lengths, then there's no way. Let me just check. Okay, I can even. Okay, if two strings have unequal lengths, then they cannot be equal. So once you check that they have equal lengths, you would go through every characters, right? Every character in one string in the corresponding character in the corresponding index in the other string, and then you would check that all those pairs are equal. And then if they are, then they're the same. Otherwise, they're not. So we can see from that process that checking if two strings are equal takes n time, where n is the length of the two strings. So yeah. Now let's consider checking if two integers are equal. So we consider integer comparison to take O of 1 time, right? Technically, it's like if you wanted to think about how integers are compared, it would compare the bits, right? An int has 32 bits. So then if each pair of bits are the same, then that means that the two ints are equal. So like 32 is like we consider it to be constant time, right? It doesn't vary with like the length of the string like strings do. So that's why we say it's constant or O of 1 time. But of course, this like puts the limitation on the things we can compare, right? We can only compare things of like a certain capacity. We can't compare insanely big numbers. They have to be able to fit in 32 bits, and then we can compare them in O of 1 time. So this kind of motivates us to be able to represent a string as an integer, which would allow us to compare strings much faster. So let's try to do that, right? So let's say we have this string from a few slides ago, ACHXF, and we have this conversion table where each character is mapped to a distinct value, right? A is to 1, and then Z is to 26, and so on. So here we just use these mapped values to convert this string into a base 27 number. And I use base 27 because like that's just the minimum base that is required to be able to fit 26 digits in like yeah, so that's how I computed this 5-digit number in base 27. And then the thing is that we would probably want it to be in base 10, right? Because when we like code in programming languages, we are working with base 10 numbers, if not like some base 2, some power of base 2. So we need to convert it to base 10. Right, so if you're unfamiliar with base conversion, basically you can think of it as our base system is in base 10. So the place values are like the units digit is 10 to the 0 or 1, and then the next digit to the left is 10 to the 1 or 10, and 10 squared or 100 and so on. So if we're using a different base like 27 in this case, then you would just, the rightmost digit would still be 1, and then you would just multiply by the base to get every successive base value. So to convert this into base 10, you would just add up this digit times its place value plus this digit times its place value and so on. Right, so that's what we've written out here. And then if you evaluate this expression, you would get this number in base 10. So we can kind of say that this number is a hash of this string. And it's important to, or like noteworthy to note that every string, like if we use this process to convert a string into an integer, every string would be mapped to a unique integer, because and like that comes from the fact that our base is larger than like the digits that we use, right? Like if you change any character or like any combination of characters, you can't end up with the same number. Like if we were to instead use like base 20, use a base like 10 or something, but still retain these digits, then it might you might lead to collisions. Like let's say we're in base 3, then you could like increase this by like 9. No, you could increase this by 1, this digit by 1. So instead of an H, you have an I, and then change this 24 into a 21, right? Then that would actually lead to the same like hash. Like if you, ACHXF would have the same hash as ACIUF, right? But once we have a base that's like 27, that's like larger than all the digits we need, then we can ensure that each string is mapped to a unique integer. So that will be important later. And so we say that we have hashed the string into a numerical hash of this. So if we repeat this process for other strings, such as on like slide 2, I think, then we can check if the strings are equal in O of 1 time, but simply comparing their hashes instead of the strings themselves. So then you have to ask the question how this is useful, because it took us O of n time to compute the hashes in the first place. So like we didn't really like speed up the process. So there are cases where like computing a hash for many strings is useful. Like pretty much in competitive programming, you'll have to be pretty much using a rolling hash to see like the advantage that hashing has over just like naive string comparison. So yeah, but we'll get into rolling hash later. So let's look at what happens when we hash longer strings, like elephant. Okay, so I've just computed the hash for you. It's going to be this number. So we see that this is quite large, and it does not fit into 2.1 billion, which is the largest value an int can store. So and this is only length 8, right? So it's because of like the exponentiation of the hash, right? Like you have 27 or whatever base you use to the power of the length. So clearly that quickly grows very large. So then you run into a problem where you can't do constant time comparison. And like maybe like intuitively you think of using like a big integer or something, of storing like very large values. But if you do that, that actually defeats the purpose of hashing in the first place. Because if you think about how you would compare two big integers, right? You pretty much are just going back to doing string comparison. You just check if every pair of digits is the same. So like going back to big integer wouldn't actually get us anywhere. So what we do is we actually apply the modulo operation to our hash. So modulo just means x modulo y is the remainder when x is divided by y. So for example, 9 mod 4 is 1. Okay, so yeah, we mod our hash, mod a large prime modulus. So a pretty common one is 10 to the, 10 to the 9 plus 7 or 1,000,000,007. So for example, in this case, modding this resulting hash by the mod will lead to this like final hash. So yeah, then this ensures that all of our hashes are less than this value, which would allow us to do a comparison because they'd fit in an int. So then remember from a few slides ago that the reason why we could just compare two strings using their hashes is that every string leads to a unique hash. But then obviously when we introduce the mod, that destroys that property, right? You could have two strings as I have listed here. These two strings being modded using the process before will lead to these hashes, which is fine because they're different. But then if you take the mod 1,000,000,007, they actually result in the same hash. So if you try to compare these two strings, like ignoring the fact that they have different lengths, it's possible to construct two equal length strings that actually have the same hash but are different strings. So yeah, so in this case we have two different strings that have the same hash modded, like when you take this mod. So then we say a collision has occurred because two different strings have the same hash. So usually in most problems you can neglect the chance of collision because assuming your mod is already pretty large, then like there's a pretty low chance. Or if you have two strings, assuming that like you can think of the computation of a hash as just generating a random number, then the probability that two different strings have the same hash is just 1 over the mod, right? If you think it was just like randomly assigning, so that's pretty low even when you have like many strings being compared. So but if you wanted to be absolutely sure, right, that two strings are equal, then you have to do a true equality check, which is just checking if the original strings are equal. So if two strings have different hashes, then they're for sure different. But if two strings have equal hashes, you have to do a true equality check to check if they're equal. So one other way of making the chance of collision even smaller is using multiple moduli, which is just the plural of modulus. So two common moduli are 1,000,007,000 and 1,000,009,000, but like really any large prime modulus is a good mod to use. So then every time you just you compare two strings, you would check like both of their mods. Like, I mean, both of their hashes for the respective mods are equal. And then this basically, like, before we had like 1 over 1,000,000,000 as the chance. Now we have like 1 over 10 to the 18th as the chance of collision. So that just like reduced the chance by a lot more. So okay, I hope like does anyone have any questions over like the conceptual concept of hashing so far? So the thing with hashing is that like even though you might like get how it works conceptually, it definitely helps to have the code or like to see code implementation of it because it definitely makes a lot more sense when you see the code written. So basically this contest is like basically it has all hashing problems. So it's just basically meant for you to practice hashing. So I'm actually gonna right now I'm gonna go through how to code this problem, how to solve this problem, but you can try the rest of the problems by yourself, like after this meeting. So here's a different problem. It's actually like a problem that we used from a previous contest. So like you can watch William's solution if you get stuck. So that's pretty nice. And then also the third problem is not a problem. It just is a link to more problems. So here's just more like challenging advanced problems that involve hashing. So like from our Clemens contest, problem 13. And then hashing doesn't appear that often in USICO, but like it has appeared two times that I know of here. So it's definitely like a pretty nice technique to know. And next meeting, which will be after we come back from Thanksgiving break, I'll like go over how to do this third problem over here. And then, but like for all these problems, you can just look up the solutions yourself if you want to like get help or are stuck. So let's first go over this question. So Sanjay has a favorite word, and in English class, he's asked to read a passage. And then we want to compute how many times Sanjay sees his favorite word in the passage. So basically, if we think about just doing naive string comparison, right, then like you have to go through every substring of T that's of length S, and then do an S times string comparison. So that'll pretty much be like if we just treat like s and t as the length of the string, so it'll be s times, t minus s times s, right? So that would be like, obviously the worst case is that if s is 50,000 and t is 100,000. So that would be like pretty big. So with hashing, we can reduce the time of this solution by a lot. So this is a pretty like classic example of how we can use rolling hash. I'll basically try to illustrate how like the concept of rolling hash works. So let's actually pull up Sketchpad. Okay, let's open a new. Okay, so let's actually illustrate, like let's illustrate the computation of a hash as like a graph where the x-axis is the indices of the string, okay, and then the y-axis is the exponent of the base. So in a like if you remember from the slide where we convert like to the base conversion to compute the hash base 10, it will look something like this, right? Like it just increasing, like every successive place value is like one higher than the last. Okay, so I think last time it may have been like flipped, but like, it doesn't matter. Like if you do like this, it's the same concept. So like I just listed like this because it'll be more convenient for my implementation. So let's say we have like a length, like we have the whole string is length 10, but the substring that we're currently considering is just the first 5 indices. Okay, so rolling hash basically means like computing a new hash based on a previous hash without having to like recompute everything. So if we're trying to if we have the hash of the first 5, like the substring that's the first 5 indices, and we want to shift it to the next 5, or like not the next 5, but shift it one to the right, then we want it to look like this, where like you would shift everything, but like of course you need the heights, you want the heights to like remain the same, and this would be gone, right? So to shift everything, we realize that we don't have to recompute, we don't have to do these 5 computations again. We can actually just look at the previous one. We can knock off this, like the leftmost thing here, then divide the rest by the base, which in dividing the rest by the base would just like shift everything down by 1, right? Like if you have like let's actually pull this example back up. Like if we had knocked off the 6 and then divided the rest of the number by 27, that would like reduce all these exponents by 1. You would have 27 to the third, and then 27 to the second, 27 to the first, 27 to the 0. So if we just subtract off this last digit and divide the rest by the base, then that's essentially like getting rid of this last digit. But then of course we need to add on the next digit. We want to add on this next stack here. Let me just finish drawing this. We want to add on this thing, right? So we have to add on something here. So to do that, we could just like pre-compute. You would basically have to pre-compute all the exponents of the base. So like here we would add on like the value that like whatever value of the character this is, like using where like some conversion table like this. You would map the value of the character times like the base to the power of the length of the string, right? Assuming you're doing like the leftmost character is being multiplied by like, the base to the power of 1, and the place value of this is base to the power of 2, and so on until base to the power of the length of the substring you're considering. So that's kind of like the idea of shifting, which is called rolling hash. So like from there we can see how like rolling hash can be used in this to kind of like go through the string, go through all the substrings of the big string T, but just every time you slide the substring to the right, you only need to do like constant time computation to compute the value of the so basically we're actually going to start implementing that, and like there'll be a lot of stuff to explain as we go. So let's just clear out this code I have pre-written. So basically let's actually close this too. So I already have a scanner and like output set up. So we first need just to read in the input. So we're actually going to read them in with this method called toCharArray. because like it'll be easier for us instead of having to do like dot char at, we can just do we can just use like access specific indices. Oh, this is it next, and then the text. Okay, so basically the first step is that we need to find the hash of Sanjay's favorite word, because what we will be doing is going through every substring of text and checking if the current substring matches, like the hash of the current substring matches the hash of Sanjay's word. So let's first compute like Sanjay's hash. We'll call it S hash. So before we do this, we actually need to pre-compute all the powers, right? Because like, for example, when we did this kind of when you do this computation, it would be convenient to have like a lookup table where we just find the base to the power of some exponent. So we're gonna declare a array called pow, and it's gonna be length. I think it just needs to be Sanjay.length, because that's the maximum power we're gonna use, right? Like every substring we consider is gonna be of length Sanjay, so it can just be Sanjay.length. And so basically, just to like clarify what this means, pow of I will need to be base to the power of I, and then mod, because like the thing with all of our operations is that we're gonna take them mod our mod. So I actually need to do some explaining about like how operations with mod will work. So here I'm just gonna set up some values. So like I used 27 before, but like it really doesn't matter what you use here, as long as it's relatively prime to your mod, which like it pretty much always will be if you have like a large prime modulus. So yeah, it's kind of just arbitrary number, but yeah. So something important with mod operations. So like I mentioned that like you would store all the mods and mod the mod, like I mean all the hashes mod this mod. But the thing is that like we have to understand how performing operations in the presence of mod works. So one thing to understand is that you will like if you have an expression, you can always add the mod at any point in the evaluation of the expression, and it will not affect the result in the given mod. So like say you have like something like 5 plus 3 and or like yeah times 4, and then we're trying to do this mod 7. Okay, so here if you evaluate what we have here is 8 times 4, mod 7 is the 32 mod 7 is 4. Okay, so let's say in here we added in a mod plus 7, which is the mod. So then we would have 8 plus 7, 15 times 4 is 60. 68 mod 7 is 4 still. So the reason why this makes sense is that like anytime you add or subtract any multiple of the mod, that would only change the result by a multiple of the thing you added. So if you add like a multiple of the mod, it'll only change the final answer by a multiple of the mod. And since like mod is a remainder, right? You can ignore any multiples of the mod, right? It won't actually affect the answer. So assuming that all the operations you're doing are only plus, minus, and multiply, but let's ignore divide for now. We're gonna come back to that. If you're only doing plus, minus, and multiply, you can multiply, add, subtract any multiple of mod at any point, and it will not matter. Okay, so so then the question becomes like, what about division, right? Like division becomes problematic because there it seems like it does matter, right? Like if you have like 5, if you're trying to do something like 6 over 2 and then mod 2, right? This would be 3 mod 2, which is 1. But if you try to add like some random thing like 6 plus 2, so you try to add 2 before doing the over 2, this would obviously change the answer, right? Like you have 8 over 2, which is 4 mod 2, which is 0. So you actually so division makes this problematic. But what we're gonna actually do is we're actually not gonna ever do division. So to do division, we're gonna have to multiply by the modular inverse of the thing that we're dividing. So I think Daniel like mentioned or was like trying to explain modular inverse in a previous lesson, but I think I will like try to re-explain it. So modular inverse is the number like say we're trying to find the modular inverse of like I think I'm actually gonna type this. So like if you have a number like a, okay, the a times the modular inverse of a in mod m will be 1 mod m. Okay, so like what this means is like, for example, if we have a number like 4 and in mod 7, so the modular inverse of 4 in mod 7 is okay, I actually don't know it right now, but I think it's 2, right? Because wait, actually, did I type this right? Yeah, so 4 times 2 is 1 mod 7, right? Because 4 times 2 is 8, which when divided by 7 has a remainder of 1. So there's not really like a, so in some cases the modular inverse does not exist, but if the base, like if the number here and this mod are relatively prime, which like you always choose a pair of base mod that are relatively prime, then you can compute this with this formula that like you don't have to completely understand, but it's basically there's this like theorem that says that if we say like I think you can denote the modular inverse as like no, okay, it's not p, it's like I just call it x. So we're trying to like find the modular inverse of a in mod m, then like the modular inverse is like wait, okay, so the modular inverse, okay, so it's basically like you can basically find it by doing a to the power of the mod minus 2. Okay, so so instead of ever doing division, we're actually going to only multiply by the modular inverse. So the reason why this is the same thing is that like if you see that when you multiply by a number and then you multiply by its modular inverse, that doesn't change the answer in the given mod, right? Because that's just equivalent to multiplying by 1 in the given mod. So if we multiply by the number and then multiply by the modular inverse, that won't do anything. So if we're trying to divide by a number, right, then that's equivalent to just multiplying by the modular inverse. I'm not sure how much sense that makes, but like I hope like this equation is apparent. Like if you kind of like, think of this as dividing by this, we're trying to like get rid of this, we can just multiply by this instead, because like these multiply to 1. So to compute this modular inverse of like a to the mod minus 2, we're gonna have to use like fast exponentiation, because like the mod is gonna be quite big, right? It's gonna be like 10 to the 9 plus 7. So let's define a variable here called mod inv. So keep in mind that mod inv is going to be base, is like the modular inverse of base mod, because we're only gonna, so this modular inverse will only be able to like cover the case of like when we're trying to like shift down all these like towers by 1, because that's equivalent of like dividing all of these by base. We just multiply by the modular inverse of base mod the mod. So we're gonna set mod inv to like expo of base to the power of mod minus 2. So to compute this, we're gonna like we're gonna use like a recursive breaking up of the exponent. So let's say like the base is b and the exponent is e. Then basically what we're going to do is compute the square root of the answer, right? And then if we multiply the square root by itself, then that would pretty much get what we want. So at every stage of this method, we would like divide up the exponent by 2. So then we can compute this exponent in just log of the exponent time. So that'll be pretty fast. So like let's call like square. Okay, first we need a base case. So obviously if the exponent is 0, then we will return 1, because like anything to the power of 0 is 1. And then we're going to take the square root, which is like that. And then here we have to check if e is even, right? Because if so like in the case that that e is even, then it's pretty straightforward. You just do square root times square root mod. So we have to do the mod because we need to keep all the numbers pretty small. And multiplying by like the mod like if this has a multiple of the mod in it, it won't affect the final answer mod. So we can just like erase any multiples of the mod that we have in this result at any step, and that will help in like keeping the number low. And also you'll notice that like I have a longs. I use long a bunch of times, even though like it seems like I only need an int, right? Because all the numbers should be with it like less than the mod, which is like within the incapacity. The reason why I make it a long is that if you're multiplying two things that are like a billion, that could like easily exceed incapacity. So long helps like keep any like intermediate results not from overflowing. And then yeah, of course, any like thing we ultimately return will be less than the mod. So in the case that e is even, I mean e is even, we have that like pretty simple case. But otherwise, we have to return square root times square root mod, but then we have to multiply by the base, right? Because there's that extra like this truncation, and then there's extra base we have to add. So this would basically compute our modular inverse for us in like pretty fast time. So it's okay. So now let's go back to computing this power array. So obviously we know that anything to the power of 0 is a 1. So we can just hard code that case. And then for the rest of the powers, we can we take the previous one. Oops, okay. We take the previous one, multiply it by the base, and then mod by the mod. Right? Because that's because like we know that anything like a to the b is a to the b minus 1 times b. So we can just multiply it by the base like repeatedly to pre-compute all these powers. Okay, so now I think we should be ready to compute the hashes. So let's loop through all the characters in like Sanjay's favorite word and then add them. So something you'll notice is that like I read the things as a char array. So like, and then I'll be using the ASCII values to compute the hash. So then it seems like it is kind of violating what I said here about like here I mapped like each, like I mapped a to 1 and so on, but like the ASCII values would be like a is 97 and so on. So then it seems like it violates the base, so it would mess up the hashing. But like it's not the exact same thing I'm doing here, but it really does not matter like what like how the values are like shifted or anything. They'll still lead to like pretty random hashes, and like yeah, it pretty much like does not actually matter. So so to compute Sanjay's hash, we're going through all the indices, and then it's gonna go up by the value of the current character times like the place value, which is power to the I, right? Here this is in backwards order, but like you can think of it as like this, right? You add the value of the character times its place value. So once we do that for all the characters, we have like Sanjay's hash, but of course we have to remember to mod by our mod at every step to keep the number less than the mod. And then now we need to go through every substring of the text. So we first need to like establish like a starting hash. Because like in order for us to do like a rolling hash, we have to start with the hash and then like build off of that. So we're actually gonna like start with a hash by like just pre-computing the hash for the text of like the substring of length s. Like the so here we would compute like this hash of that, and then from there we can build off by shifting it with the rolling hash. So we're first gonna compute this just in the exact same way we computed Sanjay's hash. So like that. Okay. So now we're actually gonna loop through all the like remaining indices. So we're gonna start at okay. So this index that we're looping over is gonna represent like the index of the character that we're adding on. So like here, if you start with like these first 5, then this first I here would be like this new thing we're adding on, right? Because it starts at Sanjay, because like the initial hash is over indices 0 to Sanjay minus 1. So we're gonna start on Sanjay over here, and it's gonna go up until the end of the text. So the first thing we need to check is whether or not like, so okay, let's first, okay, so we're asked to count how many appearances Sanjay's word has in the text. So we're gonna have like a variable for that. It's gonna start as 0, but like we need to check that if the initial hashes are equal, then we're gonna set ans equal to 1. Okay, because that means that like this very leftmost substring matches Sanjay's word itself. So we're just gonna hard code that case. And then for the remaining things, we need to shift the hash with rolling hash. So we're gonna do the process that I talked about. We're gonna like knock off this leftmost thing, which we know the exponent of that is just like base to the 0, right? So we're gonna take t hash and subtract away it's text of I minus Sanjay.length, because if I is the index of the thing that we're knocking off, then I minus Sanjay.length is like the thing that we're I is the length, I is the index of the thing we're adding on. So then like I minus Sanjay.length is the thing that we're knocking off. So that, and then the place value is power of 0. It's just going to be 1, but I'll just like make it more explicit. So yeah, we're knocking off that. Then we want to divide the rest by the base, right? But of course we can't actually do that because we have to multiply by the modular inverse instead. So we would multiply by the modular inverse. Oh, okay. Also, I mentioned here that like assuming that the only operations are plus, minus, and times, it doesn't matter if we like add or subtract any multiple of the mod at any step. So division, like the process I explained for division by multiplying by the modular inverse, works around that, because now division is actually multiplication. So like the property I said upholds, right? Because now really the only operations are plus and minus and times. So yeah, so that's kind of a reason why we need to be careful here, because when you subtract this value, like your t hash could be a negative number, and then it could cause problems, because when you have like a negative number mod some positive number, you would actually end up with a negative number, like -9 mod 4. I think it's like -3. So we want to make sure all of our things are always positive. So like here we're just gonna make sure if this is less than 0, we're just gonna add a mod to the answer, which we know will not affect our final answer at all, as long as we like mod. We constantly mod. Yeah. So this mod multiplying by mod in, I'll just like kind of comment out here. It's essentially the same thing as divided by the base. Okay. But of course we can't, like division does not actually work with hashing, because like when you multiply by a lot of things, it's like let's say you have like the number like 1 billion. Yeah, I should lost track of how many digits that was, but like you have this and then mod like 1 minus this, and then you should divide by this by 2, right? This would be like 5 and then something 4. But like if you took this mod the like 1,000,000,007, this would be 1/2, which like is not even divisible. Like that just doesn't make sense, right? So division like just does not work. You have to multiply by this modular inverse. Okay, so now the steps that we have done are okay, so the steps we've done are knock off this leftmost thing, shift all of these towers down by 1, and now we need to just add on this like rightmost tower here. So now we will take t hash and add text of I, right? We said that I is the index of the thing we're adding, and then multiply it by power of Sanjay.length minus 1, because like that's the exponent of the last thing. Because it goes from 0. If you look at how these hashes were computed, it goes from the power 0 up until power of Sanjay.length minus 1, right? So that means that like the leftmost thing will always have like place value base to the 0, and the rightmost thing will always have place value base to the Sanjay minus 1. So okay, so now that we finished transitioning the hash, right? We have the new shifted hash. Now we just need to check if this hash is equal to Sanjay's hash. And if it is, then we will increment the answer. Okay, yeah, then of course we have to, I almost forgot this, we have to mod by the mod, right? Because to keep it like under the mod. And I think that's actually pretty much the solution. So let's output ants and see if this code runs. Okay. Okay, so I retyped the data type for some reason. What is the issue with this? Oh, okay.
You add like the I is less than.
Okay, whoops. Oh wait, did I type? Wait, what?
No, it's on line 24.
Oh, 24. Okay, whoops. Okay. Thank you. Okay, so it passed both sample test cases. So let's see if it runs on the final solution. Okay, so it is accepted. So I know this is like a pretty complicated and tedious process, but like yeah, does anyone have any questions over what I did? So yeah, rolling hash, which is like what I did here, is like pretty useful in string problems. I think it's pretty common in competitive programming. So I think this is a pretty useful technique to know. And yeah, so basically there are a few other problems that you can like try on your own. So we definitely encourage you to try those problems out. Okay, so now I will share the link to the form. Okay, the link is in the chat. We want you to fill this out because, like, as I said, we will be doing a few more lectures in the upcoming weeks. So we want to kind of get your feedback to be able to cater the meetings to you. And then, at the meeting after Thanksgiving break, I will go over one of the Usico Gold question that's in the more hashing problems. Just so so these problems are actually pretty advanced, like in the like the two Usico problems I sent, or like that are in the third problem in HackerRank. Like that's a Usico Gold problem, so that means it's like pretty advanced. So and like it's advanced enough to the point where like if you can consistently solve that kind of problem, that difficulty problem, then like that means you can make Usico Platinum, which is the highest division in Usico. So, but like yeah, Usico Gold has gotten harder since those past years, like 2017. So I think that might only be like a easy gold problem, but still like a pretty advanced problem. So like if you're trying to like look for a challenging problem, I think those Usico problems are pretty good. But yeah, that's all I have for today's meeting. So thank you all for coming, and please fill out the feedback form.